In this segment, we'll examine various design patterns based on closure. Let's look first at the iterator.js file here that is in the notes. And you can see on line 17 that we build a small linked list, and then on lines 18 through 19 we traverse it using an iterator that is supplied by linkedlist.prototype.iterator, which we supply on line 3. Now, this method returns a function that works as a simple iterator. You call it to get each successive data item, as you can see down here on line 18. And the call returns null when there are no more data. Like any iterator, it needs to track its current location, which it does via current initialized to the list's first node on line 4. But here again we have a closure. Current is a local variable of iterator, not of the anonymous iterator function returned on line 6. But the anonymous function retains the execution context of the iterator call that created it, and thus has ongoing access to current on each call in its various statements here. Now, an important point. Each time we call iterator to create an iterator function, there will be a new execution context, and a new function object is created each time with scope pointing to the new execution context. So each created function object will have its own current, in other words. Each time a function block is executed, we get a new function object with its own scope property. But by the way, the actual code, which is a big piece of data, is shared and commonly referred to by all function objects created by that block. We begin to see that closure is a means of creating function data collections, in effect, small objects. Let's extend that a bit with a better iterator design. In iterator2.js, we return a full object with 4 function properties, identical to the ones you were asked to write in an LMQ in the inheritance module. So review those. Has next returns the next item, or indicates whether there is a next item. Advance advances to the next item. Current returns the current item, and reset returns the iterator to the beginning of the list. Now, while the LMQ that you wrote set up a separate linked list iterator constructor, we have no such here. Instead, our iterator function simply creates a small object with anonymous function properties that do iterator options using the curnode variable via closure. And here's an important point. When multiple functions are created under the same running execution context, they all share the same scope value. In particular, no separate copies are made of the execution context. So, for instance, in our case, when advance moves curnode forward, has next sees that change. And closures are now looking more and more like small objects. We can arrange multiple functions in the same closure. And of course, we might have several variables in the closure too. In fact, to make the iterator work, it turns out we need another local variable to go with curnode. To see why, look at the print on line 22 after the reset call. As the comment indicates, it prints undefined. Now, why is that? And let's do a quick run to confirm it, too. Yep, there it is, undefined. So, what's going on? The reason it does that is that the one local variable that is not retained in a closure is this. In many closure designs, it helps to be able to choose this when you call the function, instead of having this baked into the saved execution context by closure. So this is always determined by the object that you use to call the function, even if there is a closure also involved. In question 1, given that information, what does this then refer to during the reset call on line 21? And the answer, after a pause, it refers to the iter object that was returned from linkedList.prototype.iterator. In other words, it refers to this thing up here. Now, then why did we get undefined in that line 22 print call when we ran current? And again, coming back from a pause, well, the problem is really the reset call. There is no head datum in the iter object, this object here, and therefore it's undefined, and curnode is thus assigned undefined, and that's what we get returned from current. Okay, but here's another question. If curnode in the closure is now undefined, how come we don't get an error when evaluating curnode.data on line 9 here during the call of function current from line 22? But this is just a preview, by the way, from prior lectures, review, I'm sorry, from prior lectures. It doesn't have to do with closure per se. Coming back from a pause, well, the answer is, of course, that the double AND is short-circuited. That means that the first half of the AND, curnode, which is falsy in this case, makes evaluation stop right there. And the result of the double AND is just the value, undefined, of curnode. The second half is not evaluated at all. Okay, to fix this problem with reset, we could create another variable head in the closure, pointing to the start of the list, and then rewrite reset as current equals head. But instead, we're going to illustrate a common design pattern in closures that involve this object that we want to retain in the closure. As you can see in the now revised code, we're going to declare and initialize another variable in the closure called that, and we're going to assign it equal to this. So variable that is now a copy of this, the linked list that was the context object for the iterator call. And that will be retained in the closure. And, of course, we use it now instead of this in reset. So, JS programmers, by the way, use cute names for the closure copy of this. Probably the most popular is that, but you'll find others as well. So now any function in the closure may access the context object that was in force when the closure was created, the linked list on which we're iterating, as well as the object used to do the function call via this, and that's the iterator itself. And so we did rewrite reset with that.head instead, and that will work correctly, proving that I have a iterator 3 version that we can run with that change, and we get the correct 100 value. So here's question 4. Let's try another design variation we might have had. Could we have done this thing by putting curnode directly into the iterator object itself, as I just showed? And if so, would there need to be any changes to the rest of the iterator functions? Coming back from a pause, yeah, you could do that actually. But then curnode would be a property of the iterator object, not in the closure. And all references to it would have to be this.curnode all the way through the iterator. And importantly, curnode would then be a public property of the iterator object. One important advantage of closure retained data is that it is private. There's no way to refer to it from outside the function that has the closure. And this is one of the major reasons that closures are used in JavaScript. In fact, some JS programmers would like to use closure as an alternative to standard constructors and to new, because closure allows certain flexibilities in the use of an object's function properties and because it keeps data properties private. So consider the linked list 5.javascript file. Right there. Now, this provides a make linked list function, which works like the iterator function we were just examining, but which creates an entire linked list object from scratch via one large JSON construct, lines 20 lines 4 through 26, returning that directly. The member data of this object is the head variable, which is attached via closure, and thus shared among all the functions in the JSON object. This general pattern would work for any number of function properties, just increase the size of the JSON object, and for any number of data properties, just have more local variables in the closure. So, question 5 here. Look at this design pattern and see if you can come up with one or two advantages and disadvantages for it, based either on points already made in the lecture or on your own reasoning. It's okay not to arrive at a full list, but try to find at least one advantage and one disadvantage. And don't try to fully understand the iterator function just yet, by the way. We'll get to that in the next heading. Coming back from a pause, well, one advantage is what we mentioned earlier. The data is private now. And so we will have true privacy in a member datum. And another advantage is, as you've noticed, there's no need to use this to access the member data, just to refer to it as head. The closure supplies the data rather than the context object. And a little more subtly, there is an ability to give another part of the code limited access to the linked list by passing just one function to it. We'll see that in the next heading, perhaps. Disadvantages include there's no constructor prototype property. The whole prototype system doesn't work with this. So there's no copies of the functions are generated, so new copies of the functions are generated each time you make a linked list. Each linked list object has its own copies of the functions, and that's a problem. Now, let's take a look at this iterator function, by the way. It's the most sophisticated of the bunch. It's similar to the earlier iterator example in that it returns an object of iterator function properties, sharing a common closure that contains kernode. But the 4 iterator functions also share another execution context via closure, that of the entire makeLinkedList function, which provides the head value here, which is used in reset. So, question 6. How long is the scope chain for that reset function? Answer 6, coming back from a pause, it's 3 execution contexts long. First, the execution context of the iterator function, then of makeLinkedList, and then ultimately the global execution context. Now, this is the only example of a scope chain that long in our current topic, but the principle can be extended arbitrarily, and we'll do more like this in the Advanced JavaScript course. And then, using just the transcript for a moment here, and turning away from the notes, there is a pattern that one sees frequently in JS closure designs, which is an outer function whose sole raison d'etre is to create an execution context to be used by an anonymous function that the outer function creates and returns. Let's call this a closure generation function. Now, often a closure generation function has no name and is called once in a manner similar to the anonymous main functions we've been using in our examples recently. So summarizing it, maybe I will drop at least that much in the notes here. The classic closure generation function looks like this. And it generally appears within another function, sometimes even as the parameter of another call. So what we have then is a anonymous function, possibly with parameters, that then declares local variables forming a closure, and then returns another anonymous function, which benefits from that closure, and is the real point of this construct. You then immediately call the closure generation function, again possibly supplying parameters, and the net result is this anonymous function with its closure attached. Here's question 7. Rewrite adder.js repeated in the transcript from our earlier segment, reducing it to around 11 lines by reducing makeAdder to an anonymous closure generation function along the lines that I just described, which is called once as a parameter of the map-each call. Returning from a pause, you have the answer as seen in the transcript. We're going to stick right in the map_each_call a pattern like the closure generation function in the notes. Function and the parameter will be an increment value, and then we'll immediately return the inner anonymous function that does the incrementation by that inker, and then call with a 10 the outer anonymous function, thus creating a adder function spontaneously with the closure containing an increment value of 10, which adder function is applied by map_each, of course. This is a very common pattern in JS code, so it's one to study closely and be sure you understand.